Greetings, assembler students. In this next video, we're going to look at the assignment a little bit to compute some standard deviations, and what's going to happen is that parts of the assignment are going to go wrong. So before we see the assignment itself, we're going to ask ourselves, if I have a floating point number in the computer, approximately how many sig figs am I computing with? And here we'll be using just the float, not the double. So let's start by just assuming I have 10 binary digits, 10-bit numbers. What's this roughly equivalent to in decimal? And the way that people frequently think about this question is to ask, what's the smallest number we can add to 1.0 that'll make a difference? So you'll recall that when we added, we added 0.456 to 12.3, and essentially we were adding 0.5, and the digits off to the right of the 0.456 there we're just getting lost. So the smaller the number you add a small enough number to 12.3, it's not going to show up in 3 sig figs. Okay, so I am going to imagine here I have a 10 sig fig 1.0, which is 1.000 blah blah. I put some spaces in there for readability. And now I'm going to add 2 to the minus 10th. So 2 to the minus 10th would be that. And then when I add them, and we're assuming I have a guard digit there. One more digit off to the right so that I can, not lose stuff and then round. This will be the result. And now when I round, you'll notice that, it's like 0.5. 0.1 in binary is like 0.5 in decimal. So this 1 ends up rounding. And that's my result. Anything smaller than 2 to the minus 10th would have gotten lost. 2 to the minus 10th is the smallest thing I could add to 1. That'll end up making a difference. So what is 2 to the minus 10th numerically in decimal? Well, we know approximately, because we know that 2 to the 10th is 1024, which roughly speaking, pretty close to 1,000, which is 10 cubed, right? So 2 to the minus 10th is approximately 1 over 1,000. It's a little bit less than 1 over 1,000. It's 1 over 1,024, which is approximately 0.001. So the smallest thing that we could add to a 1 to make a difference is about 1/1000th. Which is another way of saying that it's roughly 3 significant figures of decimal. So a 10-bit binary fraction there has about the same precision as 3 sig figs of decimal when we're doing our arithmetic. So the math folks among you will notice that an easier way to get this is to say the log of 2 base 10 is 0.3010. So, that gives it to you pretty directly that, 10-bit numbers are equivalent to, it's not exactly 3010, it's a little bit more than 3010, but 10-bit numbers are going to be about 3.01 significant figures in base 10. So what we actually have for floating point numbers in the computer floats is 24 sig figs, right? So 24 sig figs, we're going to get 2 to the 24th. It's going to be 2 to the minus 24th is what we're looking for, right? Just like for 10 sig figs, we needed 2 to the minus 10th to get that smallest thing. So 2 to the 24th is what? It's 2 to the 4th times 2 to the 10th times 2 to the 10th. That's 16 times a little over 1,000 times a little over 1,000, which is about 16 million, right? It's a little more than 1.6 times 10 to the 7th. It's a little bit bigger than 10 million. So 2 to the minus 24th is a little bit less than 1 over 10 million, which means we're working with 7 significant figures, and which the number you usually see is something like 7.2. So that's how many significant figures of precision we have. Now let's take a quick look at the assignment. And the assignment is to compute the standard deviation in whatever your favorite language is, as long as you have floats. So if you have C or Java or C++, you can just declare numbers to be float. If you have Python, you can't do this because Python, they're all doubles. But there are other high-level languages too. And it's a really simple computation. And there's 2 formulas here, A and B. They are mathematically equivalent, although they're written differently. And we're going to run through both formulas in a moment here. And then I'm going to ask you to compute the standard deviations for just 3 numbers, that's all. And if you've ever taken a statistics course, you've seen some of these formulas, but you can eyeball this, and you could say standard deviation there is just 0.1. And sigma squared is going to be 0.01. And the same thing is true here. They're all of them. The standard deviation is 0.1, and sigma squared is going to be 0.01. So I want you to just compute using floats these standard deviations, and you don't even have to just write down the answers. If you want to write it on a separate document and post it up to Blackboard, that's fine. If you want to write it on this sheet and scan it or something, that's fine too. But these 2 formulas are going to give some correct results, and at least one of them is going to give some incorrect results, and I want you to analyze what's going on. So let's take a quick look at these computations. Back to our note here. Here's the 2 formulas. So formula B is the one that you're probably familiar with from class or from other statistics computations. We're going to add up xi minus x bar minus the average, add up those squares. And then we'll multiply that by 1 over n minus 1, because that's the number of degrees of freedom. So here was our 3 values. So the average of those is 1.2. You can just eyeball it, right? And now x1 minus the average is 1.1 minus 1.2 is minus 0.1. And we'll square that. We'll get plus 0.01. xi2 is dead on average, so that gives us a 0. And number 3 here is that minus the average is 0.1, so there we get 0.01. We add those up, so we add up this sum here, we get 0.02, and then we multiply that by 1 over n minus 1 is a half. Okay, and so we end up with 1/2 times 0.02 0.02 is 0.01, and that's sigma squared, so sigma is 0.1. All right, so that's formula 1. So looking briefly at formula 2, we have over here is formula A. So this is actually similar to the average. It's not the same. It's u over n. U is the sum of all the xi's. So we're going to add up all the xi squareds and divide it by n. We're going to add up all the xi's. Here we added up all the xi's and squared it. Here we added up all the squares. And basically we're going to subtract. So this sum on the left-hand side here, it doesn't want me to select nicely. This sum on the left-hand side here, this whole sum of this sum of xi squareds, and then we're going to subtract from that this one number on the right, and then we'll multiply that by n minus 1. All right, so let's go back to our notes here. So we're going to sum up the squares. So 1.1 squared is 121, right? 12 squared is 144, so that's 1.2 squared. Through 1.3 squared is 1.69. We add them up, we get that. So that is this term over here, the sum, this term over here. And then on the right we add up, u is, we add all those up. We're going to get 1.1, 1.2, 1.3, we'll get 3.6. We square that and divide by 3, we get 4.32. So on the left we had 4.34. On the right we had 4.32. We're going to subtract those, we get 0.02. We multiply that by a half, we get 0.01, and so we get exactly the same answer. Okay, so this formula, both algorithms, both formulas work. Ultimately you end up with that same difference. And in the one formula, you've got a lot of small differences that you added up, and that's how we ended up with the 0.02. And in the other formula, you had the one difference that came from basically adding up all the xi's, and the other difference that came from squaring all the averages, squaring the average many times. Squaring the sum. So, and the difference just turns out to be the same. Okay, so when you go and then do your homework, just run this through the computer and write down, or put them in a document, and then see if you can figure out, these are going to diverge at some point. See if you can figure out why they diverge. And what's scary about this is that, we're not, nowhere here are we going over our 7 sig figs. Okay, this guy should be the limit. This is 1, 2, 3, 4, 5, 6, right? So this is 6 significant figures. So we're doing 6 significant figure computations. Here's 5 significant figures. Here's 4 significant figures. You're going to be surprised when you discover, first of all, how few significant figures go wrong. And then, at the very bottom line here, how awfully wrong one of those answers is going to be. Like really, really wrong. So, see if you can, just by looking at the formulas and looking, thinking about how they got computed by hand, and then looking at the significant figures, see if you can figure out what went wrong. And the scary part is this can easily happen by accident. Okay? It's, you've got numbers that are, good to 5 sig figs, all right? Normal floats are 7 sig fig arithmetic. I should be fine, right? Well, for some computations it'll be fine, and for others it will be a disaster. And you could hit it by total accident. So that's kind of the lesson there. And with that, I'll shut up. Thank you.